All right, so we're working through proofs by contradiction. So here we go. Here's a great one for proof by contradiction. So lemma, if a is an integer that's 2 or larger, then for any other integer you pick, a cannot divide both that integer and one more than that integer, okay? So let's do some scratch work. Our scratch work, well, if I'm going to do this by contradiction, I'm going to assume the first part. So I am assuming a is greater than or equal to 2. But then I'm going to negate the second part. Remember, contradiction, we're doing P and not Q, because that's what it would take for this to be false. I would need to find an integer bigger than 2, and then I'd need to find some B where I actually do get that divides the way I want. So my not Q would be there exist B in the integers, and A would divide B, and A would divide B plus 1. Does everybody see that that's my contradiction? If I were able to find such a B, that would make this lemma false. Okay, so that's what I assume. I assume the opposite. Okay, all right, well, here we go. A divides B, that means B equals AK. A divides B plus 1, that means B plus 1 equals AL. All right, I need to get something impossible. When we're dealing with divides and factoring and stuff, if I can get 1 equals something, I can normally get my contradiction. So what I'm going to do is I'm going to take this one and I'm going to subtract the B equals AK equation, because that would give me what on the left side of the equal sign? 1. And what would I get on the right? AL minus AK. So let's factor out that A. I claim I've got my contradiction right here. What do you think? What can you tell me about the number 1 if I have 2 integers that multiply to 1? It's either 1 and 1 or -1 and -1, right? They're either 1 or -1. There's no way around that. But what was our very first assumption? A is greater than or equal to 2. So you see, this is impossible. I cannot get 1 equals 2 times something, 3 times something, 4 times something. That doesn't work if that something is an integer. Okay, that's my contradiction. All right, another way to say this is A divides 1, but A is greater than or equal to 2. That's going to be my contradiction. That's impossible. Okay, 2 cannot divide 1. 7 cannot divide 1. All right, so now we're ready for our proof. We've got our logic. Proof. Assume A is greater than or equal to 2. Now we'll say for contradiction, assume A divides B and A divides B plus 1 for some integer B. All right, and now we're back to use the definition of divides. Then there exist K and L in the integers with B equals AK and B plus 1 equals AO. Taking the difference of these, taking the difference of these yields, and I'm going to jump to that step where we had 1 equals A times L minus K. Be sure your 1 and your L's look different if you're using them both. Okay, if that is trouble for you, use a different letter than L. All right. So here we go. But the only factors of 1 are 1 and -1. And A is greater than or equal to 2. So now I'm going to put my lightning bolt, which stands for this is a contradiction. Contradiction. We have reached a contradiction. This is impossible. Okay, that's what lightning bolt means. All right. Thus, no such B can exist. And then you can, if you want, add an extra line doing the conclusion of so for every integer B, A doesn't divide B or A doesn't divide B plus 1. It's fine if you put that in or leave it off because that's what we just said, no B such B can exist. So that implies that. It's up to you. Okay, remember this is your argument to your peers, to your jury, okay, trying to convince them. What questions in that do people have questions on? All right, well, let's do another one. So here I'm reminding you of the definition of prime. So prime means it has exactly 2 divisors. So in symbols, a way to say that is it's prime. That means P is bigger than 1. And if I have something that divides P, A divides P, that thing is either 1 or P. Nothing else qualifies. Okay, so if I have something that actually does divide into that P, it must have been 1 or P itself. That's what it means to be prime. Okay, everybody okay with the symbols version of the definition? All right, so here we go. We are going to do classic proof by contradiction. This was first done by Euclid in his book, The Elements. Well, that's the first written record we have of it back like hundreds BC. Okay, so this has been around a while. All right, so if I wanted to show there are infinitely many primes, what would I assume for contradiction? Well, so there are infinitely many composite as well, right? You can have infinitely many of both. There you go. There's limited primes. There's finitely many primes would be the opposite of this, right? Okay, so that's what we're going to assume for contradiction. So I'm just going to write this proof and you'll see how it works. So assume for contradiction there are only finitely many primes. All right. Here's why we like finitely many. Because if there are only finitely many, I can list them out. So we'll say call these primes, and here's what I'm going to do. I'm going to use my set notation. So put your bracket, and they're going to be P1, P2, P3, ... till at some point Pn it ends. Okay, it has to end at some point. They're finitely many. They can't go on forever. I'm not making a claim about how long this list is. This list could be 1,000 things, 1,000,000 things, 1,000,000,000 things, but it stops. I can list them all and it stops. Okay. So does everybody understand what this notation is saying? So these are all my primes in existence I'm claiming. Okay. Now what we're going to do is we are going to create a number not accounted for on this list. And that'll be a prime number not accounted for on this list. That'll be our contradiction. Okay. So consider So I'm going to write a notation you may not be familiar with, and I'll explain what it is. So this is a large capital pi, and under it put, not p, put I equals 1, and above it n, and then on the side put p sub I. So if you remember calculus 2, the sigma, the capital sigma stood for sum, S, sum. So pi, that's the letter P, that's standing for product. So this doesn't mean add them up, it means multiply them up. So this is P1 times P2 times P3 multiplied all the way to Pn. Okay. All right. So, say now, let's write this. Each Pi divides this product. Well, I'll call it Pj so I don't double use letters. Does everybody agree? No matter which prime I pick, it's always going to divide into this product because he's part of it. I multiplied them all to get it. So whichever one, if J is 10, I say, look, there's P10 times a bunch of stuff. Okay, if J is 100, I say, look, there's the 100th prime times a bunch of stuff. So they're all a factor. Each one can be factored out. Okay, each one is part of the product. So here's the magic. All right. So now we're going to consider 1 plus this product. Well, I listed all the primes already, right? P1 through Pn, that's supposed to be all primes in existence. This number is way bigger than all those, right? Because I multiplied them together and added one. This is way bigger. So he can't be prime because he's not in the list. He's bigger than 1, so what's that mean? Well, we're not to the contradiction yet, but what type of number must he be? Composite, okay? And then we're close to the contradiction. This number must be composite since it is larger than all of our primes. Nope. And I don't want to specify, and you'll see why. Yeah. I don't want to specify what that J is. Now, if it's composite, what does that mean? What's composite mean? It has more than 2 factors. It can factor. It has to have a prime that it factors into more than just itself, right? It has to factor into primes, okay? So at least 1 pj, so this is why I don't want to specify, divides 1 plus the product of the pi's. It's composite, so one of my primes has to be in its factorization, okay, when I factor it. But wait, what did we just prove in the lemma? At the top of the page, what did we prove? Yeah, a number can't divide an integer and that integer plus 1. We proved that. And yet here, no matter what prime it is here, this pj, if he's the 10th, I come back to this fact and say, wait, but I said every single one of these p's divides that product. So if p10 divides the 1 plus, he also divides the original. Say, well, it wasn't p10. Okay, if p100 divided the plus 1 thing, he also divided the product. Either way, it's an issue. I don't care which prime it was, it's an issue. Okay. But this contradicts our lemma. This contradicts our lemma. So there are a few ways to go with this contradiction. You could say, so that means our new number we created is prime. But if he's prime, then I didn't get them all in my list, right? Or you could just jump and say, so, you know, there aren't finitely many primes, right? But so let's say we cannot have only finitely many primes. Because if there are finitely many, I can create a new one. I just created a new one by multiplying them and adding 1. That's actually a way you can find new primes. If you don't skip any in the middle and you multiply them up and add 1, you've got a new prime. Okay. The problem is if you skip some in the middle, then it doesn't necessarily work. Okay. All right. The book proof of this is slightly different the way they word it because they didn't prove the lemma first. So they kind of have to combine all that logic into one proof. It's nice to separate out that lemma and then come in here so we can just use the fact right away. Okay. Subscripts. Yeah. Yes, the I and the J are subscripts. I know it's hard to tell without lines. So just because I had to call the primes something. So lemma means this is a fact I'm going to use in my next proof. Okay. That I want to just be able to reference it. Yep. And some bigger proofs will have multiple lemmas. So they'll have lemma 1, lemma 2, lemma 3, and then they'll do the big proof and reference by lemma 1, da da da, by lemma 2, da da da. So yeah, that's what lemma means. What else? Yeah, so contradiction takes some getting used to. But the idea is showing that the opposite of the statement is impossible, right? That's what we keep doing. Okay. So that means I'm multiplying them all together. So let me do an example. So let's say I'm claiming the primes stop. Let's list our first few. 2, 3, 5, 7, 11. Let's say I'm claiming that's where they stop. Okay. When I multiply these together, oh crap. All right, I can do this. So 21 times 11 would be 231 times 10. So the product of all these would be 2 times 3 times 5 times 7 times 11. If I did that right in my head, would be 2, 3, 1, 0 instead of summing. The P for product. Yeah, instead of S for sum. All right, so when I add 1 to that, that is actually a prime number. It should be, because that's what this is saying. Okay, so that means I can't list all the primes and stop, because I can always create another one, as long as my list doesn't skip any. So my next one, I'd have to include 13. Multiply the 13 in there as well. Add 1, I'll get another prime. Multiply the 17 in there as well. Add 1, I'll get another prime. Well, so that's what we showed here, because we showed if it was composite, then I have some prime that divides both it and the product, which contradicts what we showed up here, saying nothing can divide both the number and one more. Yeah. Yep. Does that kind of help? That one? More comments, questions on that one?